All right, in this section we talk about comparing two population proportions. The first thing we have to talk about is the type of sampling methods. So in chapter 5, you might remember we talked about independent and dependent events. And so similar to that, when we're looking at independent sampling, this means that an individual selected in one sample does not dictate who will be chosen in the second sample. And the opposite is true for dependent sampling. So if an individual is selected and it affects who's chosen in the second sample, then we call that dependent sampling. Oftentimes we call, or oftentimes we use something called matched pairs samples when we're doing dependent sampling. This would be something like twin studies, where you sample maybe one person and then the second person you choose is their twin. This could be husband and wife study, studying like, do husbands and wives have differing opinions about various issues. This could be something where siblings, like brother-sister relationships, are studied. So let's jump into some examples. So example 1, we want to determine whether the sampling method is independent or dependent, and then determine if the response variable is qualitative or quantitative. All right, so a review of chapter 1. So part A, 25 pairs of twins are surveyed on their voting preference for a political candidate. Okay, so the twins right here is indicative of it being a dependent sampling. And one person is surveyed on whether they support a certain political candidate, and then their twin is asked the same question. Okay, so this is qualitative, right? No numeric values are involved in this, so it couldn't be quantitative. B, do individuals who make fast food purchases with a credit card tend to spend more than those who pay with cash? So to answer this question, a marketing manager randomly selects 30 credit card receipts and then 30 cash receipts. So something to know is when they chose the 30 credit card receipts, it had nothing to do with the 30 cash receipts. So this is independent sampling. And they're trying to determine if the credit card receipts had a significantly higher dollar amount, and that's indicative of that being quantitative. Okay, part C, a researcher wants to know if more students from private schools plan to attend college versus students who attend public schools. The research randomly samples 100 students from a public school and asks them, do you have plans to attend college after graduating high school? The researcher also randomly samples 100 students from a private school. So also notice here that the sampling of the 100 students from the public school had no effect on the people chosen from the private school in the other sample. So this is independent sampling. And asking whether they have plans to attend college is a qualitative type of variable. Okay. Part D, are the products purchased on Amazon less expensive than those purchased online at Walmart? So to answer this question, researchers randomly identified 20 products at both stores and determined the selling price at Amazon and the online Walmart store to determine if there was a significant difference in the price of the goods. Okay, so price is definitely quantitative. And this is dependent sampling, since whatever products they're looking at Amazon, they're looking at those same products at Walmart. So if they're looking at the price of a Nintendo Switch at Amazon, they have to look at a Nintendo Switch as well at Walmart. So that's why it's dependent sampling. On this problem, we're going to look at comparing two population proportions. And when we do that, we call one population proportion P1 and the other P2. So for this section, for studying two population proportions, we do need the samples to be independent of each other. We need both samples to come from normally approximated populations. So that second criteria right there gives us a good idea if that's true or not. And the third thing is we need the samples to be less than 5% of the population size. So you'll notice the subscripts 1 refer to the sample for the first population, and the subscript 2 refers to the second population sample. All right, so in example 2, in a randomized double-blind clinical trial, double-blind meaning the participants and researcher are both blind to who's the control group and who's receiving the treatment. Okay, so rats were randomly divided in 2 groups. Subject 1 received the new vaccine, while subject 2 received a control vaccine. Okay, so after the second dose, 114 of 653, so this is about population 1, experienced fever as a side effect. And then after the second dose, 71 of 534 of the subjects in the control group experienced fever as a side effect. Okay, so what I have circled in orange is about the second sample. Does evidence suggest that a higher proportion of subjects in group 1 experience fever as a side effect than the subjects in group 2? So we're simply asking, is P1 greater than P2? So this is our alternative hypothesis. Okay, so in part A, we need to verify that those 3 criteria are met in order to move forward with our z-test. And so I will say, for every problem we encounter, including the final exam, these 3 criteria will always be met, and you'll just need to check them off. You won't actually need to perform the calculations right here. Like, that calculation for both of these samples would be greater than or equal to 10. So we'll move forward. So in part B, it says determine the null and alternative hypotheses. So the null hypothesis, we always assume that the proportions from the 2 populations are equal. Or if you do a little bit of algebra, if you subtract P2 from both sides, you could say the difference between the 2 proportions is 0. So both those is acceptable. And then the alternative hypothesis, what we found right here in that second to last sentence, we're trying to see if population 1 proportion is greater than population 2 proportion significantly. All right, moving on, part C, we want to test this hypothesis. So we want to find the test statistic, and we can find the p-value simultaneously by using this calculator shortcut. Okay. So we go to the calculator, we press stat, arrow over to test, and then 2-prop z-test. Okay. So x1 is what I have circled in green, 114 out of N1, 653 sample size. And then what I've circled in orange is x2 and N2. All right, and then P1 is greater than P2 for our alternative hypothesis. And then we just go to calculator draw, typically just go to draw. And we can see the test statistic is a z-score of 1.97. And then the p-value is 0.025-ish. Right? So let's interpret this up. So if the population proportions are equal, right, that's what we're assuming in the null hypothesis, one would expect a sample difference proportion greater than the one we observed in about 0.025 times 1,000 is 25. So 25 out of 1,000 repetitions of the experiment. Okay. And just as a visual on the normal curve, that shaded area is our p-value. And part F, state the conclusion. Well, our p-value is less than the level of significance, so we know we're going to reject the null hypothesis, so we can eliminate B and C. And then the only difference between A and D is there is sufficient evidence to conclude or there is not. So we know from chapter 10 there is sufficient evidence to support the alternative hypothesis that the proportion of subjects in group 1 is significantly higher for those that experience side effect, that experience fever as a side effect. In this example, we're trying to compare the population proportions for Catholics versus seculars in terms of if they're in favor of the death penalty for people under the age of 18 that have committed a crime. So for the Catholics, the sample size is 580 and 180 indicated they favor capital punishment. So that's X1. And then for the seculars, 600 is that sample size, and then 238 out of that sample size, so that'd be X2. So part A says determine the sample proportion for each sample. Okay, so that's P hat. So we want to calculate P1 hat. So this would be 180 out of 580, which is 0.310. Okay. And then P2 hat for the seculars would be 238 out of 600, which is 0.397. So just right off the bat, we can see there's a higher proportion, at least in the samples, for the seculars that favor the death penalty for people under the age of 18. So we're trying to ultimately determine if there is a significant difference in the population proportions. So on part B, just need to make sure it verifies those 3 requirements, which it always will for the homework problems in the final. The alternative hypothesis, just like on the previous example, we assume that the proportions for both populations are equal or the difference is 0. And then we're trying to determine if there's a significant difference in the proportion for Catholics versus secular. So we say P1 does not equal P2 for the alternative hypothesis. Okay, and then we're going to calculate the test statistic and the p-value just at the same time using this calculator shortcut. Okay. So we press stat, arrow over to test, and then 2 prop z test. All right. Okay, so X1 was 180 for the Catholics that favored the death penalty out of 580. And then X2 was 238 that favored the death penalty for out of 600 seculars sampled. And the alternative hypothesis is that P1 does not equal P2. We go to draw, and the test statistic is this z-score of negative 3.10, and then the p-value we can see is 0.0019. All right, so since the p-value is less than the level of significance of 0.01, we will reject the null hypothesis that there is sufficient evidence to support that there is a significant difference between the Catholics and seculars who support the death penalty for people under the age of 18 that have committed a crime. All right, so we can also conduct a confidence interval test between 2 population proportions to determine if there's a significant difference in said proportions. So on this example, we're trying to compare males to females and determine. We're going to construct a 95% confidence interval to judge whether the proportion of males that have at least one tattoo differs significantly from the proportion of females that have at least one tattoo. So this is the alternative hypothesis, that if there's a significant difference, P1 does not equal P2. We assume P1 does equal P2 in the null hypothesis. Or again, the difference is 0 between the two population proportions. All right. So we're going to conduct a 95% confidence interval. All right. So this time we press stat, arrow over to test, and then 2 prop z interval. All right. Okay, so we're going to let P1 represent the proportion of males. Okay, so that's the sample size. And at least 181 out of that sample size have a tattoo. Okay, so we put that in the calculator. All right, and then P2 is going to represent the female population. So 1,097 females were sampled, and 143 is the X2 value. That said they had at least one tattoo. All right. We're not going to mess with the sea level because it is 95% confidence. And that's our confidence interval right there. So lower bound, negative 0.009, and the upper bound, 0.048. So let's interpret this. So we are 95% confident that the difference in the proportion of males and females, right? So this difference right here, that have at least one tattoo is between negative 0.009 and 0.048. Because the interval includes 0, right? 0 is inside this interval. We do not reject the null hypothesis. Right, because we assumed in the null hypothesis that the difference was 0. So since 0 is included in the confidence interval, we do not reject the null hypothesis. So there's no significant evidence to support the alternative.